Assalamualaikum warahmatullahi wabarakatuh. I will talk about introduction part. For our group project introduction, this project focuses on designing a centrifugal pump for river water at sections. Centrifugal pumps transfer mechanical energy into hydraulic energy through an impeller rotations. For our project objective, we want to develop an efficient pump design that satisfies the required operating conditions. Okay, for our design parameter considered, the flow rate of the pump must be 0.005 to 0.002 meters square per second. Our pump head, the size must be 50 until 100 meter, and the impeller must be geometry optimizations. For the performance evaluation, we are using velocity triangles, velocity triangle analysis, Euler pumps equations, and dimensional analysis.
For design specification, we have been selected three design that we want to observe the power output. So for the table one, as you can see, the fixed parameter that we use, which is a flow rate, expected heat, inlet absolute flow angle, inlet blade angle, outlet blade angle, inlet blade width, outlet blade width, inlet radius, and rotational speed. So this is a fixed design within the range maximum, minimum, and maximum that have been stated in the project instruction. So in the table two, we have changed the inlet blade radius and outlet blade radius to see which design have better power output for the centrifugal pump that meet the requirement. And for design one, for analysis, we can see that velocity is shown in figure one. We know that absolute flow angle it give 90 degree. So VR1 is 90 degree to U1, and for the angular velocity, we use the formula 2 pi n over 60, which is n, we already set the parameter is equal to 2500 RPM. And after that, it gives the value of 261.80 radius per second. And after that, we find the uh, inlet blade velocity, which is U1, is equal to R omega, and we insert the inlet radius, which is 0.05 meter, and we get 30.09 meter per second. So because absolute flow angle is 90 degrees, so we assume that V theta 1 is equal to 0. And to find the VR1, which is a tangential velocity, we use equation Q equal to VR1 multiplied by A1, which is area. So for the area, we use formula 2 pi RB, which is B is a thickness, inlet thickness for design one. So to find area, we use a formula 2 pi RB1, and it gives the answer of 0.011 meter cube. And after that, after we rearrange the equation, so we get the VR1 is equal to 0.091 meter per second. And for the uh, outlet velocity triangle is shown for the figure 2. We know that the blade angle is equal to 40, and from the figure, we know that U2 is equal to X plus V theta 2. First of all, we must find the outlet velocity, which is U2 is equal to R2 multiplied by omega. And we already know the angular velocity, which is 261.80 radius per second, and we just multiply by the outlet blade radius, which is 0.1 meter. And after that, we know the outlet blade velocity is equal to 26.18 meter per second. And after that, we find the radial velocity for outlet, and we arrange the equation, and it will give the VR2 is equal to Q over A2, and area for the outlet is 2 pi R B square B, and the blade thickness for outlet is 0.025 meter. And after we rearrange the equation, we got the VR2 0.0625 meter per second. And from the velocity triangle, as I say just now, for the outlet velocity is equal to v theta plus x, but we must find the x value. So we use trigonometry, and we got the x equal to VR2 over tan beta 2. And we just insert the value, and the answer give for the x is 0.074. And after that, we find the v theta 2, which is equal to u2 minus x. And v theta 2 will get the answer 26.11 meter per second. And after all the parameter we have got, we can find the theoretical head, which is the formula ht equal to u2 beta 2 over g, which is g is a gravity of the fluid. And after that, we got the ht. After we just insert the value, we got the ht 69.968 meter, which is in the range of the theoretical head. And for the power of shaft, we use the equation P equal to rho Q multiplied by U2 V theta 2 minus U1 V theta 1. And I said before, V theta 1 is 0 because the absolute fluid angle is equal to 90. So we just ignore for the V theta 1. So the equation is P over rho Q multiplied by U2 V2. And we just insert the equation, and we got the power for design 1 is 688.56 watt.
Okay, my name is Muhammad Ismazim bin Muhammad Asrin. My matrix number is CD220059. Today I will present about the design 2. First, for the design 2, key parameters is flow rate 0.001, expected head is 75, inlet blade angle is 60, outlet blade angle is 40, inlet blade width is 35, outlet blade width is 25, inlet radius is 40, outlet radius is 105, and lastly the rotational speed is 2500 rpm. Okay, for the compute result is first one is the angular velocity, which is 261.80 radian per second. Inlet blade velocity is 10.472 meter per second. Outlet blade velocity is 27.49 meter per second. Inlet radial velocity is 0.114 meter per second.
Outlet radial velocity is 0.0625 meter per second. Outlet wave velocity is 37.55 meter per second. For the theoretical head is 77.20. For the shaft power is 757.35. And lastly, the efficiency is 99%. Okay, now I will present about the dimensional analysis for design 2. The first one is the head rise coefficient is I get is 0.28. Second is the floor coefficient. The result is 0.00048. And the third one is power coefficient. I get 0.00013. And lastly, the efficiency is 99%.
So this is the specification for design 3, which is the key parameters. The Q is equal to 0.001 meter cube per second, and the expected head HA equal to 75 meters, and the inlet blade angle beta 1 is equal to 60 degree. The outlet blade angle beta 2 equal to 40, and the inlet blade width B1 equal to 35 mm, and the outlet blade width B2 equal to 25 millimeters, and the inlet radius R1 equal to 30 millimeters. The outlet radius R2 equal to 110 millimeters, and it will rotate at 200 and 500 rpm. So as for the computed result, we obtain that the angular velocity is 261.80 radian per second. The inlet blade velocity U1 equal to 7.854 meter per second, and the outlet blade velocity U2 is equal to 28.80 meter per second. The inlet radial velocity VR1 equal to 0.152 meter per second. The outlet radial velocity VR2 equal to 0.0578 meter per second, and the outlet velocity V theta 2 is equal to 28.85 meter per second, and we obtain that the theoretical head is equal to 84.70 meter, and the shaft power is equal to 830.88 watt, and we get the efficiency is approximately 100% efficient. I think that's all from me. Thank you. After complete the calculation, as for design 3, we get the head rise coefficient is 0.303. As for the floor coefficient, we get 0.00048, and the power coefficient CP we get 0.00014, and as for the efficiency we get 100% efficient.
So for the design one, it is meet the project requirement, which is the pump flow must be between 0.005 meter cube per second and 0.002 meter cube per second. And also the pumping head range is equal to 69 meter, which is still in the range of the project requirement. And angular velocity of the return speed to 2500 rpm, and it can give the angular velocity value, which is 261.8 radian per second. And for the blade tip, it gives the velocity 13/06 meter per second, and the outlet blade velocity, which is 26.18 meter per second. So it gives the as a velocity increase, it gives the outlet that indicate that kinetic energy is being passed effectively from the impeller to the fluid, and it relative low hydraulic power output, which is a 680.56 watt, and the minimum power will give and produce the excellent energy efficiency and directly driven by the outlet impeller dimension and will moderate the rotational speed.
Okay, now I will present about the discussion design about design two. The first one is flow rate and head. The design two meets the required range of 0.005 minus 0.002 meter cube per second at Q 0.001 meter cube per second and deliver a theoretical head of 77.20 within the 50 to 100 M operating window and close the 75 M design target. Second is the velocity triangle analysis with R1 40 mm and R2 105 mm. Blast velocity rise from 10.47 meter per second at inlet to 27.49 meter per second at outlet. This velocity increase confirm effective energy transfer from the impeller to the fluid. The outlet wear velocity or V theta 2 equal to 27.55 meter per second is obtained via velocity triangle analysis. The third one is the power and efficiency. Shaft power of 757.35 watt is relative low, indicating the design achieved the desired head at modest energy cost, and dimensional analysis yields 0.28, CQ is 0.0048, CP 0.00013, and a theoretical efficiency of 99%. And lastly, for the overall assessment, design to satisfies all project requirement, correct flow rate, head within the prescribed range, and near perfect theoretical efficiency. The moderate rotational speed and compact impeller size contribute to the acceptable power consumption.
As for design 3, the discussion for design 3, design as for the flow rate and head, design 3 target the same Q, which is 0.001 meter cube per second, and achieve a theoretical head of 84.7 meter, higher than design 2 and comfortably within the 50 to 100 range. The larger outlet radius, which is R2 equal to 110 millimeter, contributes to the increased head. And as for the velocity triangle analysis, with the R1 equal to 30 mm and R2 equal to 110 millimeter, the design shows a larger velocity spread, which is U1 equal to 7.85 meter per second, rising to U2, which is 28.80 meter per second. The outlet velocity, which is V theta 2, which is 28.85 meter per second, is the highest among all three designs, driving the superior theoretical head. As for the power and efficiency, um, shaft power of 830.88 watt is the highest in the study, a natural consequences of the higher head output. Dimensional analysis gave CH equal to 0.303, CQ equal to 0.00048, CP equal to 0.00014 with a calculated efficiency of approximately 100% efficient under ideal condition. So for overall assessment, Design 3 delivers the highest head, which is 84.7 meter at reasonable power, which is
830.88 watt. Critical efficiency approach 100%, confirming excellent performance under ideal assumption. The design satisfied all project requirement while demonstrating that the smaller inlet radius with larger outlet radius effectively boosts head output. That's all for me. Thank you.
Next, for conclusions of our projects, we have found that 3 centrifugal pumps design were successfully analyzed and evaluated. First, all design achieved the required flow rate and pump head range. Our pump also, the design 3 produced the highest head, which is 84.70 meter, but required the highest power. For design 1, had the lowest power requirement, but lower head performance. For design 2, design 2 was selected as the optimum design due to its balanced head generations, power requirements, and efficiency. Lastly, the project highlights the importance of impeller geometry for an optimization in centrifugal pump performance.